We live in a volatile world, which sometimes feels hopeless, but I am here to remind us of certain qualities of humanity that bring us back to hope, that allow us to imagine a more beautiful and more harmonious world, a better world, a more just world in which we can all thrive. The main point I would like to make is that mathematics brings us closer together and unites us. Why do I say that? Every mathematical formula or theorem expresses a fundamental truth about nature, about the universe, but also about ourselves, about who we are. These truths are persistent, unchangeable, and eternal. They do not change with new advances in technology or with some new information that comes to light. They are all part of our common cultural heritage. And most importantly, these mathematical truths, they belong to all of us, regardless of our language, religion, our culture, our upbringing, our skin color. These mathematical truths are universal. They belong to all of us equally. There is this democracy of mathematical truths. There is this equality of mathematics, the way it applies to all of us. And mathematical truths mean exactly the same thing to all of us, regardless of who we are, where we come from. So that's the way in which we could say mathematics unifies us. I would like to emphasize this quality of mathematics, and I want to contrast, say, mathematics and literature. So just think of your favorite author, of your favorite book. So I grew up in Russia, in the former Soviet Union. So for me, it's natural to think of a Russian author, say Leo Tolstoy, and his book, Anna Karenina. If Tolstoy did not live or died before he wrote this book, nobody would have written exactly the same book, right? But if Pythagoras had not lived or died before he discovered Pythagoras' theorem, someone else would have come up with exactly the same mathematical result. Pythagoras' theorem is about the right triangles on a plane. It's a famous relationship, a squared plus b squared equals c squared, between the lengths of the sides of a right triangle having 90 degrees. And in fact, we know that the same theorem was discovered in many other cultures around the same time, and perhaps even earlier. That's the kind of universal truth aspect of mathematics that I'm talking about. Mathematical truths are necessary and persistent, and they stay the same. Pythagoras actually lived about 2,500 years ago. There is an interesting story about him, that the name actually comes from the two Greek words, apith, which is the older name of Delphi, where there is a famous temple of Apollo with a famous inscription, "Know thyself." Pythia was an oracle who delivered prophecies from the god Apollo. And agoras means to speak publicly. So Pythagoras is the one who speaks on behalf of the oracle. It's very interesting, and we'll keep this in mind. But he lived 2,500 years ago, and already at that time, his disciples, Pythagoreans, understood this beautiful statement about geometry. And the statement has not changed. There is no reason to believe that it will change. It's not like next year is going to be a squared plus b squared equals c cubed. No, it's still going to be c squared. How interesting, huh? Oftentimes, mathematics kind of gets lumped with physics, and people kind of think of them in a very similar way, but I would like to contrast mathematics and physics. Physical theories get updated in time, you see. In 17th century, Isaac Newton came up with his laws of motion and his law of gravity, which served physicists for over 200 years. But eventually it was understood that these laws break down as we go to smaller distances or higher energies, or when the force of gravity becomes too strong. So these theories had to be updated. We had the advent of quantum mechanics, Einstein's special relativity, Einstein's general relativity, and the search is still on for a unified theory of physics. But mathematical theories do not change. They're objective, necessary, and timeless. So how interesting, right? So physics describes the physical universe, but what does mathematics describe? And that is sort of my main point, that mathematics does not come to us through our five senses. Mathematics does not come to us from the physical reality. And we can already see that in Euclidean geometry, which most of us have to, had to study at school. Objects of Euclidean geometry are points, lines, triangles, circles, like the ones I have drawn here. But in fact, whatever I can draw on a piece of paper, or in this case on my iPad, is actually only an approximation to idealized abstract objects which are the true characters of Euclidean geometry, and to which the axioms and theorems of Euclid apply. Indeed, if you look here, my lines, no matter how hard I tried, my lines are a little bit wiggly. They're not exactly straight. My points have a size, right? But in Euclidean geometry, a point should not have any size. A line should have no thickness. Every line has to be exactly straight, not wiggly, and it has to go to infinity in both directions, you see. So this shows us that, in fact, we cannot have this idealized abstract lines, triangles, circles, points, and so on in the physical world around us. After all, physicists tell us that the universe is about 13.7 billion years old, give or take. And the speed of light is finite, so the observable universe is finite. We cannot see an infinite line in it. But in Euclidean geometry, it is postulated that such lines exist. And some of the axioms of Euclidean geometry, the famous fifth postulate, is about those infinite lines in their entirety. The fact that there exists a unique line passing through a point outside of a given line that is parallel to it. There is no way we could observe that in the physical world around us. We do not perceive mathematical objects through our five senses. For the vast majority of mathematical objects, we can't even find traces of them at the moment anyway. In the physical world around us, there are some higher dimensional or even infinite dimensional geometric shapes. There are esoteric numerical systems like p-adic numbers that we study in mathematics. There are very large infinite sets, the so-called inaccessible cardinals. Where do we find them in the physical world? And my contention is we don't. We don't observe them in the physical world. But what does it mean? This has a very important implication. It means, as the great logician Kurt Gödel said, that mathematical ideas form an objective reality of their own, which we cannot create or change, but only perceive and describe. And Charles Darwin went even further. Charles Darwin, the great biologist who came up with a theory of evolution, actually wrote in his autobiography in his later years that he had deeply regretted to not have proceeded far enough to understand something of the great principles of mathematics, for people thus endowed seem to have an extra sense. And I kind of agree with that. But I would argue that not only mathematicians have this extra sense, but all of us do. We're all mathematicians, after all. You know, Picasso famously said that every child is an artist. And the question is to preserve that sense of being an artist as we grow up. And I would say every child is a mathematician. It's a very precious sense of wonder. Being a mathematician is, first and foremost, is about the sense of wonder, the sense of awe, the sense of not being tired of being surprised, of looking at the world with fresh eyes and imagining things that we cannot even see around us. That's what mathematics is about. And that is a kind of an extra sense, the sixth sense, if you will, in addition to the usual five senses by which we perceive the world, that we all possess, even though it may be dormant in us or underdeveloped. But in principle, we can cultivate it. That's what education is about. That's why math education is so important, that we all get access to the treasures of mathematics, you see. But the most important thing is that I do believe that Charles Darwin was right, that there is this sixth sense, there is this sense of the mind by which we reach and find those mathematical objects. That shows you that mathematics can be thought of as a kind of a source code of the human mind. While physics describes the external physical world, mathematics describes our inner mental world. You see, because we just talked about the lines, the points, the triangles, and so on of Euclidean geometry. And we see that in the physical world around us, we only can observe their approximations. And yet, when I teach this in a classroom in Berkeley, nobody ever asks us, Professor, what do you mean by an infinite line? What do you mean by a line which has no thickness? What do you mean by a line which is not wiggly? Everything in the physical world around us is wiggly. We have no trouble, we have no problem conjuring this mathematical idealized abstract objects, conjuring them up, imagining them in our minds. And the way we do it is exactly the same. How interesting, exactly the same. We perceive mathematics in the same way. And I would argue that this points to the fact that our minds are actually connected. And that means, my dear friends, that we are all connected to each other at a much deeper level than is ordinarily understood. And that's what, in my opinion, gives us hope. Because we can now go from the sense of being separate, of being alienated, of being small, to the sense of unity, to the sense of connection, that we are all connected to each other. Since we have this capacity to imagine, we can use this capacity to imagine a better world, to let our hope to fulfill itself. If you want to hear more about these ideas, I point you to my YouTube channel and my series of videos called The Aftermath. But what I want to finish with is this idea of imagination, the idea of a dream. We should not be stuck in the world as we observe it today. That's what mathematics shows us. Mathematics shows our capacity to imagine, to conjure things up, seemingly out of nothing. Sofia Kovalevskaya, which was a great mathematician at the end of the 19th century, she was the first woman mathematician to receive a doctorate degree and to be a professor at University of Stockholm. In a very short lifespan of about 40 years, she made some very important discoveries in mathematics, and she became a model and a beacon for women around the world to express their capacity to doing mathematics, to become mathematicians alongside with men and with everybody. So that's another sense in which mathematics is, there is a sense of equality in mathematics, that anyone can have access in principle to mathematical theorems and mathematical formulas. They cannot be patented. There are decisions by courts in various countries saying that you cannot patent Pythagoras' theorem. Nobody can take it away from us. Nobody can steal it from us. It belongs to all of us. It's an amazing archipelago of knowledge, which we all share. And so many people to these days are kind of cringe when they hear mathematics, because they probably may have had some bad experience in the classroom when they were kids and so on. But how interesting that it is mathematics that points us in the direction of our unity, in the direction of our connection. And in this regard, Sofia Kovalevskaya wrote, many people who have never had a chance to know what mathematics is about and think of it as just basic arithmetic, consider dry and fruitless subject. But in fact, it's a field that requires most of all imagination. You see, it is not possible, she continues, to be a mathematician without being a poet at heart. It seems to me that a poet should see what others can't see deeper than others. And that's the job of a mathematician as well. In other words, mathematics helps us to see deeper, to see the invisible. I want to mention Srinivasa Ramanujan, a great Indian mathematician who received mathematical formulas, astounding mathematical formulas in his dreams. The family goddess, Hindu goddess Namagiri, would come to him in his dreams, write those formulas, and when he would wake up, he would write them in his notebooks. What a remarkable story, which again shows the plasticity of the human mind, our ability to receive mathematics through this sixth sense that Charles Darwin was talking about. There is a beautiful film about Ramanujan and his mentor G.H. Hardy, which is called The Man Who Knew Infinity, with Dev Patel and Jeremy Irons. Interesting enough, G.H. Hardy, who was a Cambridge professor who took Ramanujan under his wing, it's a beautiful story of love and mentorship. He wrote about Ramanujan's discovery that they must be true, because if they were not true, no one would have had the imagination to invent them. Again, you see, imagination, our ability to imagine. And I would like to close with a quote from another great sage, Albert Einstein. Imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world, stimulating progress, giving birth to evolution. In this volatile world, sometimes it's not even clear what we can hold on to. It seems that the world is ridden with conflict and strife, and we naturally get depressed and desperate and feel small and lonely. But mathematics, in my opinion, has this important and yet largely untapped spiritual function. Mathematics, if we look deeply into it, if we understand the nature of mathematical ideas, the nature of mathematical theorems and formulas and so on, if we look through the history of mathematics, we see that mathematics does give us hope. It shows us our ability, our capacities, which are beyond what is ordinarily understood, which, by the way, what separates and distinguishes us from the machines. That's another interesting question, that understanding our mathematical ability also brings us back to the sense of dignity, to the sense of agency, that we are not machines, we are not computer programs. We are capable to imagine, we are capable to love, we are capable to being compassionate. And it is with this understanding that I look to the future with hope. Thank you very much.